Before we get to this one, I want to make one thing crystal clear. What we're discussing in the next few minutes, that is, why as a box rotates at a consistent rate, its vanishing points will slide more rapidly or more slowly depending on where they are on the horizon, is not something you're likely to understand immediately. You're not expected to. I'm adding this disclaimer during my editing because I realize that while I do mention this, it's after the explanation. Many of you may find yourselves confused and may rewind to the beginning to rewatch that section over and over without ever having reached the part that clarifies that you're not meant to fully grasp it right now. This is going to be something you will encounter multiple times throughout this course. Concepts may be explained that you will not fully understand immediately. Some students find that to be quite frustrating. It's quite normal to want to understand everything in its entirety before attempting to apply it, in order to avoid mistakes. But as I explain at length in Lesson 0, this is how the course is designed. Do not try and bend the course to the way you would like it to be. Follow it as it is designed and accept that concepts will be understood gradually by doing the exercises. By making attempts, by making mistakes, and by allowing those mistakes to help others understand what we do and don't quite grasp so they can fill in the gaps. What we're covering here is honestly less significant than most of the things we cover. It's really just an explanation as to how the consistent rotation of a 3D form results in an inconsistent displacement of its vanishing points. It's worth going through, but completely unnecessary in order to apply. In fact, much of what I explain here, I only came to understand in the last couple of years by reflecting on the concepts that I was teaching students and through conversation with other instructors, namely Aline Fouard, an instructor of perspective and human anatomy at l'École supérieure de réalisation audiovisuelle in Paris, France. That was a good while ago, so they might not actually remember. Anyway, long story short, I didn't even understand this as a student or as a working illustrator and concept artist, so don't get hung up on it if you don't either. And with that, let's get started. Normally, we look at perspective scenes from the eyes of a hypothetical viewer, or out of a camera lens looking out onto the scene. But we can actually make a bit more sense of this concept of rotation and how it impacts the vanishing point's positions by looking at everything from above. So here we can see the viewer and the box they're looking out at. Let's add in a horizon. Remember, the horizon line is meant to represent an infinite distance away from the viewer. That means that every point along the horizon is an equally infinite distance away. Given that all these distances are equal when measured from the viewer's location, rather than representing the horizon line with a straight line, we can represent it as a circle with the viewer at its center. Now for this last piece, you'll have to bear with me. Here we have the box represented as a rectilinear square or rectangle, meaning that their lines are set at 90 degrees to one another. While normally this is correct, we're not trying to draw the box itself from a top-down view, but rather we're trying to understand what the viewer is seeing, and more importantly, why. In order to do this, we introduce the vanishing points as seen by the viewer, which will result in some deformation from our current abstracted top-down point of view. So if you recall, I explained that as our given sets of edges turn in space, or in this case, as the whole box and its two horizontal sets of edges rotate, the vanishing points that are already off to the side will slide further along the horizon line, whereas those closer to the middle will slide less. When we view the horizon line as a circle, however, all of the vanishing points move by a consistent amount, regardless of where along it they are. Thus, this inconsistency can be understood as the result of the flattening of the horizon. Before we can illustrate this, we first need to correct our diagram a bit, as the relative distance between the viewer and the object and the circular horizon are incorrect. Between the viewer and the object, we have a non-infinite distance, but between the object and the horizon line, there is an infinite distance. That is, because the horizon is infinitely far away. This means, and those of you who are not mathematically inclined will just have to trust me on this one, that we can effectively say that at scale, the distance between the viewer and the object is basically zero in the face of the full distance between the object and the horizon. This allows us to combine the positioning of our object and viewer, which is necessary to demonstrate how the vanishing points behave as the horizon is flattened. Getting back to that, given these vanishing points on the circular representation of the horizon, if we want to understand where they'd fall on the flattened horizon, we can simply draw a line from the viewer through the given vanishing point and see where it intersects with the flat horizon line. Note as well what happens as these vanishing points slide along the circle, and how it impacts their positioning along the flat horizon line that the viewer sees. Along the top, you'll see the same from the viewer's eyes. As the box rotates, the right vanishing point accelerates as it moves away from the center of the frame until this line extension runs perfectly parallel to the flat horizon line and perpendicular to the viewer's angle of sight. We consider this vanishing point to be at infinity, and any lines that are meant to converge to it will remain parallel when drawn on the page, as the viewer now sees. Conversely, as the vanishing point on the left moves towards the center of the frame, it slides along the horizon more slowly. Now that you're all properly confused, here's the kicker. Very little of what I just painstakingly explained actually matters. Why? Perfect perspective is not better, nor is it more useful than good enough perspective. It is, however, more cumbersome, and worrying about it will get in the way. For our purposes through this course, where we're not worried about things being perfectly correct, but rather close enough, we needn't worry about exactly how much the vanishing point should move. All that matters to us here is that the more our edges rotate, and the closer they get to being perpendicular to the viewer's angle of sight, the further out to the side that vanishing point will move. And as an extension of that, when our edges are fully and perfectly perpendicular to the viewer's angle of sight, the vanishing point will be infinitely far, resulting in the lines that represent those edges on the page never converging and remaining entirely parallel, both in 3D space as edges and in 2D space as lines. This is how we get to something you may have heard of if you've studied anything about perspective before: 2-point and 1-point perspective. Just remember, there's no such thing as 0-point perspective. So you should never be drawing with all your vanishing points at infinity if your intention is to replicate what humans see. And just to get in before someone calls out, well, isn't isometric or axonometric projection 0-point perspective? No, they're not. They do not fall under perspective projection and do not share its goals. They exist in their own category and cannot be referred to as perspective in the context of projection. This confusion usually arises from people using perspective as a synonym for projection, which is incorrect and very misleading. Just like the distinction between edges and lines, as well as shapes, which for our purposes refer only to two-dimensional elements like circles and squares, and forms, which refer to three-dimensional elements like spheres and boxes, the wording we use to describe what we're doing is important. Moving on, let's explore how this concept of vanishing points at infinity results in the 1, 2, and 3-point perspective grids people talk about when discussing perspective. It is not saying that an entire scene can be represented with just 1, 2, or 3 vanishing points, because that would only allow for 3 sets of edges with 3 specific orientations. Rather, it's a way to talk about 3-dimensional space as a grid. This kind of grid can be used as a reference. If you know what your major axes are, you can estimate how an arbitrary diagonal would be laid across if your spatial reasoning skills are developed far enough. It also happens that a lot of human structures adhere quite closely to grids. There will always be deviations, but if you think about a building, they're pretty boxy. That's how we end up with these kinds of simplifications. What I want you to keep in mind most of all, however, is that regardless of whether you're talking about a 2-point perspective grid, where one set of edges, usually the vertical one, is drawn with parallel lines that do not converge, or about a 1-point perspective grid, where 2 sets of edges, usually the width and height, are represented with parallel lines on the page. Each of these are still dealing with 3 distinct sets of edges, and therefore they're always dealing with 3 individual vanishing points. It's just that some of them are at infinity, but they still exist. We still need to be thinking and talking about them as they exist, whereas the terminology of 1-point and 2-point perspective tends to make us ignore them, which I find really hurts the development of our underlying spatial reasoning skills. Of course, far be it from me to strike such common phrasing from the student artist's dictionary, so I'll settle for doing my best to clarify what they really mean. All of this can certainly be kind of confusing, and a lot of people will be left asking, well, when should I use 1 or 2 point perspective instead of 3 point? There are two answers to this, with one of them simply being that the number of vanishing points you keep in mind, whether 1, 3, or 862, depends on the number of sets of parallel edges in the object or scene you're drawing, but that's not a terribly useful answer. There is, however, a rule of thumb that I can offer to help you make a bit more sense of what 1 point, 2 point, and 3 point perspective really tell us about the space in which we're working. It comes down to thinking about a single box in the world and considering how it's oriented in relation to the viewer. If the box is rotated such that we're looking straight into one of its faces, or close enough to it, then you can think of this box as being drawn in 1 point perspective, with the other 2 vanishing points being at infinity. If the box is rotated such that we're looking straight into one of its edges, or again, close enough to it, then you can think of the box as though it's drawn in 2 point perspective, with one of its vanishing points being at infinity. And lastly, if the box is rotated such that it's really more one of its corners that's pointing at the viewer, then it's drawn at 3 point perspective. All of its vanishing points are concrete as opposed to infinite, and all of your sets of parallel edges will converge when drawn as lines on the page, rather than remaining parallel in 2D space as well. This is easy enough to apply to a single box, but if you're trying to think about what kind of grid to use for an entire scene, the box you're thinking of for this rule of thumb formula would be set at the orientation that is most common across the objects in your scene, or a rough average of the objects in your scene. I can't really say this enough. These are just simplifications, and while they can help us out towards the beginning, it is important that you get used to the idea of thinking less in terms of specific point perspective grids, and more about the idea that there's a vanishing point, whether concrete or infinite, for every set of parallel edges in the scene, and that a vanishing point goes to infinity when it is oriented perpendicularly to the viewer's angle of sight.